Hey, calculus. I'm so thrilled to have another AMI day. You could just tell by my enthusiasm. E- Anyway, today we're going to, well, there'll be two questions like normal, so look through those throughout the video. But we're gonna touch base on the 5.4 stuff. I really wish I didn't have to go through and teach new stuff via virtualness, because I know videos aren't really the best thing in the world to learn from, but I trying my best. I really wish that we didn't have AMI days, but it beats doing a Kahoot and teaching yourself. So for those who fill out the Google form and actually have questions to ask, thank you for that. That helps me a lot. Because if you just put no, no, and then that doesn't really tell me if you learned the stuff or not, or if it makes sense. Usually I can tell based on conversational stuff, but since we can't have a conversation, we gotta do what we gotta do. So actually, I'm going to be going through some of the questions that people had on the Google Forms. So follow along in the notes, and that's going to be very helpful for you. But first, let's talk about from the notes 5.4, numbers 1 and 2. It's going to be going over the second derivative test and what that actually means in terms of things. So firstly, this is the equation we're working with, the 1/3 x cubed minus x. And below, in example 2, they actually gave you the graph, or they made the graph based on a few assumptions. First off, we kind of know what this graph is going to look like because it's an x cubed and it looks like John Travolta. Even better, we already know it had two different, or one x-intercept really. So, anywho, let's take actually no, it had three x-intercepts, but it doesn't even matter. What does matter is what we can get from its derivative and its second derivative. Now, firstly, a second derivative determines if your graph, that portion of your graph is going to be concave up or concave down. Now, what does that mean, actually? Well, this pink graph right here tells you exactly what a concave up graph is going to somewhat look like. And this one right here is going to be a concave down graph. Now, just because it's concave up or concave down doesn't mean your first derivative is going to be the same signs. Because if you take a look here, because first derivatives determine your slope, right? And slope is determined by reading left to right. So be very, very careful about reading left to right. So here, reading left to right, you're starting by going down. Even though the arrow is pointing up, you got to read this left to right, which is going to be decreasing. Here, it's going to be 0, so your derivative is 0. And here, it's going to be increasing. So even though your derivative, your first derivative, changes sign from negative to positive, your second derivative is positive here. So being concave up means that your second derivative is positive. On the flip side right here, concave down, reading left to right, let's take a look at the first derivative. It's increasing because reading left to right, even when the graph is pointing downward, you're reading left to right, you're increasing, you're going up. Here it's going to be 0, your first derivative. Down here, it's going to be decreasing, but meaning your first derivative is negative. However, because it's concave down, your second derivative is always negative here. And that's what the second derivative test actually gives us. So firstly, let's take a look at x cubed minus x. So now, the first derivative, doing the power rule, right? You get x squared minus 1. So that means that you're going to be able to factor it, set it equal to 0. So that way you can figure out when the turning points are going to be. So then you can factor it out, x plus 1, x minus 1, x equals negative 1, x equals 1. So we know that we have turning points on this graph at x equals positive 1, x equals negative 1. Because that's what the first derivative tells you, is that you have a slope of 0 of a tangent line, which is what the 0 thing means right here, is that drawing a tangent line, you got the slope to be 0 here. Now, what the second derivative tells you is whether or not you have this term called a point of inflection, or POI is why they like to determine that. And that POI tells you if your derivative or your second derivative is going from positive to negative or negative to positive. So taking a derivative of x squared minus 1, you just get 2x. And I don't think it's a shocker. Solving it gives you x equals 0. So we got these turning points and we got this POI. But how do we get all the other stuff from that? Well, firstly, you can determine whether if it's increasing or decreasing, because those turning points could have been flip-flopped. So you could have actually done the thing we like to do, which is set the intervals, -1, negative infinity to -1, -1 to 1, and do it that way. However, the second derivative test is supposed to tell you, or is supposed to help you out and make things more efficient. So doing it the old-fashioned way, you could just kind of pick some points there and determine if your slope's negative or positive and do the little roller coaster thing. Or you could also take the second derivative test. So taking the second derivative test actually cuts our work by a lot. Because instead of having to do -1 to negative infinity, -1, -1 to 1, or 1 to infinity, all you have to do is set your x equal to 0 for your second derivative and only set up 2 intervals here. And then determine whether or not what the signs are. So here, taking a look at the second derivative test, negative infinity to 0, plugging in a number between that, take -1, plugging it back into here, you get a negative answer, meaning you're going to be concave down at x equals, or from negative infinity to 0. You take a look here, sure enough, you are actually going to be concave down from negative infinity to 0, meaning you're pointing down, looking like this little parabola going downward. And from 0 to infinity, right here, taking a look, plug in a number between 0 to infinity, x equals 1, plug it back in here, you get a positive answer. So from 0 to infinity, your graph is going to be concave up, meaning it's going to be looking like a smiley. Positive answers, right? And this x equals 0 is a point of inflection, meaning it's changing your concavity at that very specific point, meaning it's not concave up or down at x equals 0. It's neither. It's actually switching, because if you think about it from this way, it is going to be concave up because it's looking like a smiley. And this is looking like a frowny, but what happens in the middle? Point of inflection. And that way, you can kind of think of it like that, so you don't have to do your increasing, decreasing intervals that way and save you a bunch of time. If you do it that way, I mean, it works because plug in a number between -1 to 1, you get a 0, or you get a negative answer, meaning you're decreasing, and positive, negative, positive. You take a look at that graph. Or you can do the concavity test and then save your work, because you could also get the graph from that. And that's that whole section. So question number 1 from the Google form is going to be, what's a fun math memory you've had? We've been together about a year and a half, with the exception of one. So what fun math memory do you have from this year or last year? It could be either. So yeah, share that in the Google form as your question 1. And then there you go, question 1. Now the second thing I wanted to do in this video was go over one of the homework questions. So thank goodness that people have homework questions. And if you have any other questions too, feel free to stop by the office hours. I'll be chilling. I was lonely last time, no one showed up to the office hours, so I was Jay chilling. I could have been at the gym, you know, on that grind and getting gains. But I want to go over one of your homework questions from 5.4. So let me erase all of this, and then we'll get started. And it's going to be number 18. So we'll be going through number 18 together on this board, and I'm making some room for it, so don't at me. And let me just write it in a better color than blue, because even though it does show up pretty decently on the screen, it doesn't show up on my eyes that well. So we're looking at g of x equals x cubed over 3 minus x squared minus 3x. And our objective on this question is to use the second derivative test to find the local extrema for the given function. Show the analysis that leads to your conclusion. So it's actually exactly like we just did, only a little bit more nuanced. So we want to determine, and we could do the old-fashioned way by just doing it with the first derivative test, but regardless, let's get through it and then see what the local extrema are. So firstly, take its first derivative. I don't think that's a shocker. It's kind of cherry picked for us here. And let me use a different color, may as well. Because it's got that fraction on it, meaning that 3 is going to cancel out with the 1/3, which makes things a lot easier here. Yep. So there we go. That's our first derivative test, and I think we're going to need to set equal to 0. But off to the side, we can also take its second derivative while we're at it. Just to kind of do 2 birds with 1 stone. So g double prime would just be 2x minus 2. Perfect. And then we'll use that second derivative test to help out with the extrema stuff. But firstly, let's figure out where our local extrema are. So whether or not setting our first derivative equal to 0 here. So doing that, I think we can factor it. So x minus 3, x plus 1. So x equals 3, and x equals -1. Now here, a valid way to do it is the first derivative test, right? So you can set up the intervals with -infinity to -1, -1 to 3, and then 3 to infinity. And you could do it this way. This is probably the safer way to do it. That way you don't have to kind of think doubly about it. But here it wants us to practice using the second derivative test to determine our local extrema. So here, let's do it that way. So let's set the second derivative equal to 0. So factoring out 2, 0 equals 2x minus 1, so x equals 1. And only set it up with 2 intervals. So from -infinity to 1, meaning 1 to infinity. And if you notice a pattern, right? The point of inflection that we're looking at is actually halfway between these two values. One is right in the middle between 3 and -1, if you really think about it. If you think about the other one too that we did on the board, sure enough, yeah. And that's just based on the symmetry of numbers. So it's pretty cool how it happens that way. Now that we got these intervals set up, let's do some sign checking. Plug in a number between -infinity to 1. Let's plug in 0. You end up getting a negative value here. And if you plug in a number between 1 and infinity, you get positive. Meaning if you're to kind of sketch out the graph a little bit, which is what she does with those tables and stuff, then you can determine whether or not what your local extrema are going to be, whether it's going to be a max or a min. So this helps you determine if you got maxima or minima. So being concave down means you're going to look something like that, meaning you're probably going to have a local max at the -1, because -1 falls between -1 or -infinity to 1. And here, since it's going to be concave up, you can determine that between 1 and infinity, it'll be concave up, meaning you're going to have a local min at 3, because 3 falls between that value, and it's got to be a concave up. So this is just a shortcut way of determining whether or not you're going to have a min or a max, and that's what the second derivative test tells you. So you're going to have a local min at x equals 3. So, and it wants you to find the value, so plug it back in. So g of 3, because I'm lazy, I'm just going to use what it has for us and trust it. You get -9. So that's going to be a min at 3 -9. And then here, they're going to have a max at x equals -1. So max at x equals -1, and then plug in -1 here, you're going to end up with a 5/3. So you got a max there. -1 and 5/3. Cool. All right. So your second question you have to answer on your Google form is actually an interesting one. It's going to be a mathy question, I'm sorry. But in pre-calc, we kind of went over the formula for the axis of symmetry. And the axis of symmetry is for a quadratic. It's that x value where you have that symmetry. Now we have some calculus under our belt now. So I want you to determine the formula which the formula is x equals negative b over 2a. But with calculus, I want you to determine how we can get that. And hence, I'll give you the first hint for that. So I want you to explain it as best as you can. This is the standard form of a quadratic. So how would we determine, oh gosh, there we go. So how would we determine the axis of symmetry formula based on that? So how do we get from this to this, in other words? Explain that as question 2 in your Google form. Let me know if you have any questions. I'll be available by email. Feel free to stop by in those office hours. And yeah, take care. I'll hopefully see you on Wednesday. So.